Poštovane koleginice i kolege, pozdravljam vas u ime organizatora ovog kongresa i izložbe. Zahvaljujem na pažnji i na prisustvu i da krenemo polako sa ovom sesijom Pametni algoritmi za pametne zgrade, upravljanje sistemima. Jedna oblast, jedna tema apsolutno orijentisana ka budućnosti i koja treba sutra, preksutra da pomogne što boljem funkcionisanju sistema klimatizacije, grejanja i hlađenja. Prvi rad koji ćemo imati danas je integracija sistema upravljanja zgradom u jednom porodilištu. Vrlo interesantna tema, s obzirom da se radi o primjeni building management sistema za upravljanje zgradom i to u jednom porodilištu za koje se smatra da ima posebne zahteve što se tiče uslova, što se tiče temperature, vlažnosti i kvaliteta vazduha. To će nam prikazati kolega Andrej Duna.
Hello everybody, my name is Andrej Duna and today I'm going to present you my paper, Integrating a Building Management System within a Maternity Hospital. So, importance of BMS in healthcare buildings. Basically, hospitals consume 2 to 3 times more energy than standard commercial buildings. HVAC alone accounts for 50 to 60% of hospital energy use. BMS reduces energy waste by 15. Oh, sorry about this. BMS reduces energy waste by 15 to 25% through automations. It ensures stable climate and provides centralized alarms. Now, the project. It's a new hospital located in Timișoara. It has a basement, a ground floor, and 4 floors. This project involved integrating a full building management system during construction, ensuring all HVAC lighting and monitoring systems were planned, wired, and commissioned together for maximum performance. Now, the basement accommodates the reception area for emergency patients, administrative functions, and a space is designated for instrument washing and sterilizations. The ground floor houses the in vitro fertilizations unit as well as 2 obstetrics and gynecology wards. The first and second floors are designed for rooming in wards where newborns remain in the same room as their mothers, supported by facilities that include infant washing stations within each room. The third floor is dedicated to the ICU, providing specialized intensive therapy services. And the 4th floor contains the operation block together with anesthesia and intensive care department. This image shows an operation room inside the maternity hospital. In the center is a surgical table surrounded by ceiling-mounted surgical lights and equipment pendants used to supply medical gases, power and instrument trays. Now this image shows an operation room inside the maternity hospital equipped with modern surgical and neonatal care infrastructure. In the center is the operating table. Above it, a circulated ceiling-mounted pendants provide medical gases, power outlets, and support brackets for equipment positioning during procedures. This image depicts a hand washing and preparation area used by medical staff before entering the operation room. Now, this is the main page of the BMS. Here you can see the floor selection menu for accessing room levels controls, quick access buttons to the heating station, cooling stations, and AHU pages. Now, this page facilitates the heating stations. As you can see, you have set points for the boilers. You can set them to manual or auto. Automatic control functions through sensors and thermostats, so the building knows what's most efficient for it, cooling or heating. This is a diagram that shows you actual boilers and pumps, temperatures, pressures, and you can check if everything it's okay. Basically, one of the cool things is basically if you have an issue, you don't have to send out a team there to check. You can see it on this dashboard and locally. This is the actual heating station that is in the hospital. Onto our air handling unit. This diagram shows supply and extract fans, heating and cooling coils, filters, and heat recovery. Just like the boiler room, you can see temperatures such as intake temperature, exhaust temperature. You can set it manually or automatic. Usually AHUs are used in hospitals to ensure clean, controlled, and reliable air conditions. Onto fan coil units. This interface shows each FCU's status, temperature set points, operating mode, thermostat state, heating and cooling demand. Again, you can set it to auto, and through thermostats it knows what to do and what's most efficient for the building, but you can always set it to manual mode. You can also control air curtains with BMS. And additional fans, it shows auxiliary ventilation fans, including basement, sterile storage, and terrace units with their operating mode, temperature set point, room temperature, and run or alarm status. Now, this is the basement level environment monitoring. Here you can see the AHUs, and you can see the FCUs too with their temperature. Again, this is just the basement level. The same interface, albeit with some changes. It's available for every floor of the building. Now, based on the fact that this building has been constructed with BMS first in mind, you can see here it lands in a pretty efficient category compared to other buildings. It's rated B at the moment. Conclusion. Basically, the integrating of a building management system in a maternity hospital has proven to be significant advancement in operation efficiency. This case study reinforces the potential of smart building technologies to transform healthcare infrastructures. As hospitals continue to expand and energy demands arise, the implementation of BMS solutions will become not only beneficial but essential for sustainable and reliable operations. Thanks.
Thank you very much. Any questions? Yes, please.
Thank you for your presentation. And also the BMS graphics were very nice, very helpful. I noticed that you use for the ventilation system that you notice where it's present, there's someone present in the room. I said that it was an access card. You are both checking if there is an access card in the house?
As far as I'm aware, there are human presence sensors in the building.
So it's human presence.
Yes.
Not sensors or something like this.
Sorry?
You don't have to sell two sensors in order to change the rates, the ventilation rate.
Well, basically, through those human presence sensors, they can turn on and off based on...
So it's an on-off system.
Basically, yeah. But you can always make something... as I said, it's automatic and manual. If there is need for light, let's say, in a place 24/7, there will be light there. It's not, yeah.
Thank you very much.
Yeah, thank you. Any
Hvala
other
lepo.
questions?
Thank you.
Thank you.
Thank you. Sljedeći rad je isto vrlo interesantan, matematički model i simulacija dinamičkog odziva temperature u zgradama. S obzirom da na temperaturu utiču mnogobrojni faktori, vrlo je interesantno onda napraviti jedan matematički model koji će napraviti predviđanje toga ponašanja. Ovaj rad će izložiti koleginica Biljana Miljković. Izgleda da nije tu. Vidjet ćemo da li će možda da malo zakasni. Sljedeće je isto što se tiče, da kažem na neki način, regulacije. Ljudsko telo kao termodinamički sistem, paralele između termoregulacije i upravljanja zgradama. The human body as thermodynamic system, parallels between thermoregulation and building management. Vrlo isto interesantno, s obzirom da u zgradama imamo building management system koji upravlja grejanjem, temperaturom i tako dalje, a naše telo ima svoj sistem termoregulacije, a paralelu o tome izložit će kolega Stelios Lampadakis. Yes, please.
Good afternoon. First of all, I would like to thank the organization committee of KGH for giving me the opportunity being here with you and share my point of view about thermal comfort. Actually, the topic is about thermal comfort. It's not about automation. But my point of view is that the most complex automation system is the human body. So we're going to have 6 chapters in my short presentation. We're going to see the significance of thermal comfort, the understanding of thermal comfort, thermoregulation mechanism, how hormones are involving to this mechanism of thermoregulation, and the health effects of thermoregulatory stress. Finally, we're going to have a small discussion and some conclusions about all this. But first of all, I would like to introduce you Kelvin. Kelvin is our digital assistant for today because I borrowed his body for my slides. So before I start, I would like to tell you that there are some physiological survival mechanisms in our body that they are essentials. First of all, it's homeostasis. Second is the respiratory system. Third is the cardiovascular system. And then it's the nervous system. And this is the priority of this mechanism for our body in order to work and survive. If we don't have homeostasis, all the other systems stop. They are not working. Then, if we have homeostasis, we are going to respiratory system. So homeostasis is more important than breathing. Of course, we have the endocrine system, immune system, digestive system, and reproductive system that they are crucial and very important also, but they are not crucial for our survival. But what is homeostasis? We hear about homeostasis, but what is homeostasis? It is responsible for our thermoregulation, the blood pH regulation, electrolytes balance, osmotic pressure regulation, glucose regulation, and hydration of the body. Respiratory system, we all know that it is about oxygenation, CO2 removal, pH regulation, respiration that supports the thermoregulation via evaporative cooling and pH stabilization. Our cardiovascular system, we know that it is responsible for continuous blood supply to our vital organs and also regulation of blood pressure and cardiac output and heat distribution to our body. And the nervous system is responsible for control of respiration, cardiac function, and the thermoregulation, also for reflex and homeostatic feedback loops. So what we see here, our 4 crucial survival mechanisms have thermoregulation. Oh, I missed it because it's a different PowerPoint, but it's thermoregulation in the 4 crucial survival mechanisms of our body. But we are talking about thermal comfort. We are all familiar with thermal comfort, but what is thermal comfort? The problem with thermal comfort is that it is subjective. Even now here, some of you may feeling that they are too hot, or maybe someone is colding. So according to ASTRA Standard 55, thermal comfort is that condition of mind that expresses satisfaction with the thermal environment and is assessed by subjective evaluation. There is no thumb rule to tell us that we have perfect thermal comfort conditions. And why is this? Let's see our body. There is a thermal zoning in our body. And every single organ in our body needs its own temperature in order to work correctly. And if we don't have this temperature, if we lose this set point, then there is an activation of the thermoregulation mechanism that it's going to bring our organ, our body, to the desired temperature. It's trying to reach our set point. We all know the thermal comfort factors are the personal factors depending on the person, such as the clothing and the metabolic rate, and also environmental factors like ambient temperature, airspeed, mean radiant temperature, and relative humidity. There is the equation of thermal balance that is fundamental for the thermal comfort, and it is the algebraic sum of metabolic rate, mechanical work, radiation, convection, clothing, evaporation by sweating, and evaporation by respiration. So if this algebraic sum is positive, it's higher than 0, then we are feeling that we are getting warm. And if it is negative, then we are feeling cold. Now we are going somewhere. We know that during the thermoregulation activation, we feel discomfort. And now, because we are engineers, we have in our mind that discomfort, it means that these numbers there are positive or negative. So comfortness is not anymore something that it is so fantastic, so subjective. It is a number. We know when we will feel discomfort or comfort. But let's make it a little bit easier for us, because we are mechanical engineers, most of us. There is thermal zoning also inside the building, just like in our body. We have different temperatures for the control room, for the server room, for the office, for the laundry or the machinery room. It's exactly like in our body. You have different temperature for every organ. It's the same in a building. And we need to maintain these temperatures. And if we don't have these temperatures, then the HVAC system, the thermoregulatory system of the building, is getting involved with the building in order to achieve the temperature we need. So we saw the equation of thermal balance, but it's almost the same like calculating thermal or cooling loads, because we have the same equation more or less. Okay, I will not spend more time in the slides. You can have it after. But if you can see, it's like calculating the thermal loads in a building. It's the same calculating the thermal loads in our body. So what do we do in a building? Usually we install sensor or thermostats inside the rooms that we desire to check. Maybe sometimes a thermostat outside the building to check the ambient temperature. We have a BMS controller, and then we are transmitting the signals from the sensors to the BMS controller, and then we have maybe a PI algorithm making some calculations, and we have an HVAC system, and transmitting back to the HV system the results of the calculations of the BMS, and then the HVAC system starts to distribute the heat or cooling to our building in order to maintain the temperature that we want, and then we have an internal loop of getting back and see how is going the system. The same exactly thing is what happens in Kelvin's body. We have the temperature control with sensors going from different parts of our body to a central controller, and then we are sending back signals of what to do. Is it possible? Yes, because, okay, we will not call them anymore sensors. We will call them thermoreceptors, okay? We have two types, peripheral in the skin and central in the core of our body. We have transmission of signal, no wires anymore, but we have alpha, delta, and C fibers. And give me just 1 minute more for this. It is like having category 6 or category 4 cables in our data. Why? Alpha delta fibers are transmitting the signal really, really quickly, with 2 meters to 5 meters per second. But C fibers are transmitting the signal very slowly, for 0.2 meters per second to 2 meters per second. What does it mean? If I take my hand and take it over a heat source, the alpha delta fibers will send the signal directly to our controller. But the C fibers will not do it because they are slow. If I keep on doing this for a long time period, let's say 1 minute, then finally the C fibers will send the same signal. So if I do it just for one time, then the controller will say that it's not significant. Don't do nothing. We don't need homeostasis here, because it's something that it's just for a moment happened. But if we keep on doing this, this means that the temperature is going to rise. So you have to do something for this. This is something like a PI algorithm that our body is having and doing it inside the BMS controller of our body. So we have hypothalamus. Hypothalamus is our controller. And using an algorithm that we're not going to explain it here, but it's similar to PI or PID sometimes algorithm. And we have the activation of thermoregulation with two types, the nervous system, that it is the emergency mode of our body, and the endocrine system, that it is the boost mode of our body. So more or less, we can see the analog between a BMS system of a building and the BMS system of our body. Now, we're talking about hypothalamus. This is hypothalamus. Actually, this is not the real size of hypothalamus, because hypothalamus is tiny. He only weighs 4 grams. But it is a central regulatory organ of homeostasis. It compares the set point of 37 degrees of our body with the actual temperature and corrects the deviation error similar to a PI algorithm. What we have as a result of these calculations of our hypothalamus, for example, vasodilation, sweating, decrease in metabolic heat production if we feel that we are too hot, or vasoconstriction, shivering, shivering, thermogenesis, piloerection, and many other reactions of our body in case that we don't have the correct temperature. But first of all, we have some different reactions, such as I'm feeling too hot, let's take off my jacket, or let's change the temperature in my thermostat, or even leaving the room because I feel discomfort here. These are called behavioral responses. And why do we have behavioral responses? Because we are feeling discomfort. And why do we feel discomfort in a room? Because of hormones. There are hormones that triggers the feeling of discomfortness. So we have adrenaline, noradrenaline, I will call it T3, okay? T4, melatonin, and cortisol. Of course, we have many more hormones involving to the thermoregulation system, but this is the most critical. I will not tell you every function of every hormone because I don't have the time to do it, but I hope that you will, if you like, to give a closer glance to my point of view. You can find it in the KGH site, I think. Adrenaline mainly has to do with our heart and our blood pressure and metabolic heat production. Noradrenaline, it's almost the same with adrenaline, but also it is responsible for, look down there, behavioral arousal. Now, you see that it is very responsible for the behavioral arousal, but I put it last there. Why? Because first of all, calibrates the blood pressure, then the cardiac output, the breathing rate, and if all that happens, then we have the behavioral arousal. The same with TAF3 hormone and TAF4 hormone. Let's see about TAF3 because it is an hormone produced in our thyroid, okay? Only the 20% of thyroid is, TAF3 is produced in thyroid gland. The other 80% is peripherally produced. How? You see, it is very important hormone, but why the 80% is peripherally? Because T4, it's going to the nerves, and then it is converts to TAF3. This is very important, and I'll give you a funny example that maybe will ask some questions that you have about your body. If you live from a hot climate, let's say from Creta Island, and go to Finland, you will feel that the first 3 or 4 days, you will feel more cold. You will colding, and after the 3 or 4 days, you will say, oh, I'm getting used to this temperature. I'm getting used to cold. You need 3 or 4 days to do. Why? Because if you see, the half-life of this hormone is 7 days. And the TAF3, it's 1 day. We need TAF3 to thermoregulate our body, but we don't have enough TAF4 to do this because only 20% of TAF3 is produced in our adrenal. So we need the TAF4 to go to nerves, and it needs many days to do it, maybe 7 days as you can see it, in order to fill up our buffers of TAF4 and then we can produce more TAP3. So we'll need these 3 or 4 days. That is the adjustment our body does to when we are changing our climate. Melatonin, you know, melatonin is very important for our for metabolic rate, of course, but for the sleep and circadian cycle. And cortisol, also, it is a booster that it is very important, and if we feel discomfort, maybe we can even not be able to lose weight if we are on a diet. So we see our body is a factory of hormones, and these hormones affect our body. We have long-term effects like problems that you can see it here. I will not say everything because I know already I have my time and maybe I'm 2 minutes more than I had, than the 15 minutes. But also we have short-term effects that it's more familiar to everybody here in this room, like arrhythmias, cardiovascular instability, hyperventilation of our breath, sudden metabolic demand, and thermal discomfort, dizziness, or even skin and peripheral nerve stress. So, the conclusions. Thermal comfort is not a luxury, but a necessary and critical demand mechanism and imperative in our body as part of thermal regulation. We are saying about thermal comfort, we want to design our buildings with thermal comfort, but what is thermal comfort exactly? Now we know that thermal comfort is essential for our health. Lack of thermal comfort will inevitably lead to health issues if sustained over a long period to our body. And indoor environmental quality is the key to ensuring a quality living space as the environment supporting the well-being of the occupants. Engineers must incorporate human-centered design principles to create a healthy building environment because HVAC is not just about air, it's about physiology. Engineers don't design buildings. We design the living experience of the human body inside them. Here you can download it, all my data and all my resources, and I will be very happy, me and Kelvin, if you send us an email and we can have a better collaboration. Here are our email. Oh, Kelvin put his email there. It was not my idea. Oh, he was just kidding, sorry. Okay.
Thank you very much for the very, very interesting presentation. Any questions? Imali pitanja? We must first understand everything and then we can set the questions.
Thank you very much.
Yeah, thank you once again. Idemo dalje. Opet jedan interesantan rad. Uticaj generisanih sintetičkih vremenskih serija na tačnost predikcije u sistemima daljinskog grejanja. Radi se o tome da se kod praćenja rada sistema daljinskog grejanja prate različiti podaci u SCADA sistemima i važno je da se ti vremenski periodi formiraju na ispravan način. Koleginica Milica Tasić.
Tako je. Dobar dan svima. Moje ime je Milica Tasić i danas ću vam prikazati rezultate istraživanja na temu uticaj generisanih sintetičkih vremenskih serija na tačnost predikcije u sistemima daljinskog grejanja. Autori ovog rada, uključujući i mene, su profesor Ivan Ćirić, Ljiljana Radović, Vladan Jovanović, Marko Ignjatović i Miloš Simonović. Glavni problem kojim se ovo istraživanje bavi jeste zapravo neregularno uzrokovanje podataka koji su posledice, odnosno rezultati merenja u sistemima daljinskog grejanja i koji se beleže u SCADA sistemu, a koji mi koristimo najčešće da primenom metoda mašinskog učenja ili nekih drugih metoda veštačke inteligencije izvršimo određene predikcije. Zašto su ovi podaci zapravo problematični? Pa zbog toga što ukoliko podatke iz SCADA sistema posmatramo kao vremenske serije, što mi najčešće praktikujemo iz razloga što su ti podaci međusobno zavisni i prikazuju promenu energetskih indikatora kroz vreme, onda upravo to neregularno uzrokovanje podataka dosta otežava modelima mašinskog učenja, pre svega standardnim modelima mašinskog učenja, da na pravi način, odnosno sa nekom dovoljnom preciznošću, mogu da predvide tražene izlaze. Dva su rešenja, tako da kažem, ovog problema. Prvo je ili naći adekvatan model, odnosno stvoriti neki hibridni model mašinskog učenja koji će moći da sa dovoljnom preciznošću radi sa neregularno uzrokovanim podacima i da radi sa neregularno uzrokovanim podacima i da daje dovoljno dobre predikcije, a drugi pogled na rešenje tog problema jeste naći neki metod rekonstrukcije tih podataka, tako da sa tako rekonstruisanim podacima možemo da radimo, odnosno da ih primenjujemo u klasičnim, tačnije standardnim modelima mašinskog učenja, pri čemu nećemo imati nekih značajnih problema tokom vršenja predikcije. Metodologija istraživanja se sastoji iz neka 4 generalna koraka. Prvo je prikupljanje podataka, dakle za potrebe našeg istraživanja mi smo koristili podatke sa SCADA sistema Mašinskog fakulteta u Nišu i konkretno smo koristili podatke o datumu i vremenu, odnosno podatke koji sadrže datum i vreme uzorkovanja. Zatim koristili smo podatke o temperaturi polazne vode u primarnom krugu i o temperaturi povratne vode u primarnom krugu. Detektovali smo, odnosno nakon što smo detektovali da u takvim vremenskim serijama, odnosno podacima, postoje praznine, izvršili smo prvo i osnovno izvršili smo projekciju svih tih vremenskih serija na jednu ciljnu vremensku mrežu, koja je na ciljnu vremensku mrežu sa uniformnim korakom od 15 minuta. Nakon toga smo pristupili modeliranju strategija, rekonstrukcije. Jedna od strategija koju smo primenili jeste lokalna Lagranževa interpolacija reda 2, a druga je generativno popunjavanje uz busta preziduala po sezonskim binovima. Tačnije, ova druga metoda jeste zapravo metoda popunjavanja podataka, odnosno tih rupa u podacima, stvaranjem sintetičkih podataka. Četvrti korak bi bio evaluacija, dakle kroz evaluaciju mi smo izvršili poređenje realnih i sintetički dobijenih vremenskih serija i realnih interpolisanih vremenskih serija i prikazali te rezultate kroz histograme, raspodelu prirasta, autokorelaciju, pasivnu autokorelaciju i vizualne grafike. Rezultati istraživanja pokazuju sledeće. Na ovom slajdu vidite vizualne grafike sa leve strane, vizualni grafik koji se odnosi na rekonstrukciju vremenske serije temperature povratne vode u primarnom krugu primenom Lagranževe interpolacije, a sa desne strane grafik koji se odnosi na upoređivanje rekonstruisane vremenske serije primenom generativnog popunjavanja. Ovako, laički gledano, mi vidimo da interpolisani podaci i generativno popunjeni podaci zapravo međusobno dobro prate jedni druge, pošto su posmatrani podaci, odnosno realni, obeleženi plavim kružićima, interpolisani su obeleženi narandžastim linijama. Ne postoji nisu vidljiva neka velika značajna odstupanja na ovim vizualnim graficima, osim nekih malih pikova koji postoje. S druge strane, kada se radi o temperaturi polazne vode u primarnom krugu, sa leve strane je primarna lokalna Lagranževa interpolacija, sa desne generativno popunjavanje, vidi se da Lagranževa interpolacija, odnosno primjena ove metode, nije u potpunosti uspela da isprati realne podatke, dok bi za generativno popunjavanje moglo da se kaže skroz suprotno, dakle vidi se da je da su ovi rekonstruisani podaci dobro ispratili realne podatke. Međutim, ukoliko malo detaljnije analiziramo primjenu ovih metoda, dolazimo do nekih drugih zaključaka. Ovde su prikazani grafikoni, histogram, distribucija prirasta, autokorelacija, pasivna autokorelacija i odnosi se dakle na poređenje rekonstruisanih podataka primjenom Lagranževe interpolacije povratne vode u primarnom krugu. Generalno, ovde su se ova detaljna istraživanja, odnosno detaljni prikaz rezultata se dosta dobro poklopio sa vizualnim grafikom. Stubići kod histograma i distribucije prirasta su se apsolutno poklopili, dakle nije narušena ni srednja vrednost podataka, niti je narušena njihova dinamika, takođe nije narušena ni njihova raspodela, dakle podaci su apsolutno identični, odnosno interpolacija je, kako se zove, uradila ono što je trebalo i apsolutno, mislim, sa nekom većom tačnošću možemo da koristimo standardne modele mašinskog učenja sa ovim interpolisanim podacima. Takođe, ako posmatramo i grafik autokorelacije i pasivne autokorelacije, odnosno konkretno autokorelacije, takođe je došlo do apsolutnih poklapanja, što znači da vremenska komponenta, odnosno vremenska zavisnost između tih podataka nije narušena, dok grafik pasivne autokorelacije, koji inače u nekim realnim uslovima treba da budu u opsegu od -1 do 1, ovde prikazuje značajno veći opseg, odnosno kreće se u periodu od -25 do 20, ali to bi verovatno trebalo da znači da je možda pre nego da smo koristili metodu za interpolaciju trebalo da izvršimo, da svedemo, odnosno da te podatke normalizujemo na opseg između 0 i 1 ili između -1 i 1, da bismo dobili dobar grafik pasivne autokorelacije, a verovatno i sutra bolju predikciju kada budemo koristili ove podatke. Sa druge strane, ovde su rezultati poređenja, histogram i distribucija prirasta generisanih sintetičkih podataka temperature povratne vode u primarnom krugu i oni se značajno razlikuju od tih podataka, značajno se razlikuju ovi rezultati od rezultata koji smo malo pre videli na vizualnom grafiku. Histogram i distribucija prirasta pokazuju kako je dinamika, odnosno prvo i osnovna srednja vrednost podataka dobijenih generisanjem, popunjavanjem je delimično, čak mogu da kažem i većim delom narušena. Veličina, odnosno širina stubića realnih podataka se znatno razlikuje od širine stubića dobijenih popunjavanjem sintetičkih podataka. Takođe i distribucija prirasta isto to pokazuje, što znači da ukoliko bismo mi koristili podatke dobijene ovom metodom u standardnim modelima mašinskog učenja, takva predviđanja ne bi pokazala realno funkcionisanje ovog sistema. Isti slučaj je i kod podataka, sintetički generisanih podataka kod temperature polazne vode u primarnom krugu. Dakle, pikovi uopšte nisu nekako dobijeni, nisu zapravo projektovani na pravi način. Stubići takođe nisu iste širine, tako da bi i u ovom slučaju sintetički generisani podaci, ukoliko bismo ih koristili, sintetički generisani podaci temperature polazne vode u primarnom krugu, ukoliko bismo ih koristili u nekim standardnim modelima mašinskog učenja kao ulazni podaci, ne bi prikazali realno stanje funkcionisanja tog sistema. Možda bi dali dobru predikciju, možda, ali pitanje je da li bi to bilo, to prosto ne bi bilo to što mi očekujemo i što bi trebalo da očekujemo ukoliko bismo hteli da ovakve metode koristimo za automatizaciju sistema. I ostalo je još poređenje interpolisanih podataka temperature polazne vode u primarnom krugu dobijeni interpolacijom. I tu se takođe razlikuju podaci, kada smo malo detaljnije ih prikazali preko histograma i ovih grafika u odnosu na vizualne grafike. Donekle je interpolacija u ovom slučaju odradila ono što je trebalo, međutim od nekog trenutka interpolacija ne dodaje nove vrednosti, nego se zadržava oko neke set tačke i automatski ponavlja te iste vrednosti. Jedino što je ovde dobro jeste grafik autokorelacije koji pokazuje da vremenske zavisnosti između podataka nisu ni u ovom slučaju narušene. Zaključak bi bio da je ovo jedna veoma važna tema, jer pravilno kombinovana rekonstrukcija neregularnih serija je ključna podloga za pouzdane predikcije i odlučivanje u sistemima daljinskog grejanja. Fokus nekih budućih naših istraživanja je definitivno usklađivanje generisanih serija sa realnim merenjima, evaluacija na više lamela, direktan AB test uticaja rekonstrukcije na performanse konkretnih modela mašinskog učenja i da sad ne zalazim previše u detalje, trebalo bi voditi računa i trebalo bi pre toga definitivno izvršiti ispitivanje koja vremenska serija sadrži kratke rupe, koja duge praznine i kako da to tretiramo.
S obzirom da se radi o velikim snagama, velikim količinama energije. Je li ima pitanja? Nema. Idemo onda dalje.
Hvala.
Sledeći je kolega Obrad Aničić, ali ja koliko vidim njega nema. Tako da idemo na predviđanje izlazne snage fotovoltaika. To je koleginica Milica Kašiković.
Thank you. Well, our work was machine learning-based prediction of PV output power. My name is Milica Kašiković, and I come from University of East Sarajevo, and I did this work with Božidar Popović and Aleksandar Anđelković. In introduction, solar energy as one of the most promising renewable energy sources play a key role in the energy transition. In recent years, photovoltaic, usually we used PV. Technology has experienced rapid development thanks to its longevity and minimal requirements and minimal negative impacts on environment. However, the production of electricity from PV systems is variable and unstable process due to fluctuations in solar radiation and the significant influence of ambient environmental conditions. Development of modern machine learning methods, especially based on artificial intelligence and artificial neural networks, has opened new opportunities for significantly improving the accuracy of electricity production forecasting in solar power plants. Artificial neural networks inspired by the functioning of biological neural networks enables exceptional capability to learn from complex nonlinear data sets. They particularly well suited for modeling time-varying phenomena such as fluctuating energy output of PV systems. On this photo we have presented artificial neural network architecture. We actually used one hidden layer because we have two input parameters and one output parameter, and we modeled this from 1 to 10 neurons in a hidden layer. For the making of this ANN model, To develop this artificial neural network model, we use data from from July to September at 1 minute time sample. But we actually, for forming a model, we used data from July and August, and for simulation of model, we used data from September of 2025. Input parameters, we have a temperature, actually ambiental temperature and solar irradiance, and target parameter was power. The idea behind this model is that solar radiation and ambient temperature are thermometeorological parameters that can be predicted with reasonable accuracy, which in turn allows estimation of power plant output in future time points. During network training, the input values are fed into neural network through the single hidden layer of neurons, and the output generated as an estimate of power at a given moment. Here in this table we can see regression coefficient and mean square error for, calculated for 2 data sets. For data set, as I said, for forming a model, training a model, and data set for simulation. With different number of neurons in this hidden layer, we didn't get a pretty much different result, but we got better result for a simulation data set. Based on the table, it can be observed that the number of neurons in the hidden layers does not have a significant impact on the model prediction accuracy. It is also evident that the regression coefficient is higher and MEC lower for the networks when evaluated for data for simulation. This indicates that there was no overfitting of neural networks. On this photo you can see what means underfitting, overfitting, and optional model construction. Here we can see regression coefficient for training, testing, and validation process. And we can see that not all results follow the optimal curve, but and these are due to other factors, maybe some spikes in temperature and wind speed, maybe a cloudiness or something like that. In conclusion, in real world, predictions of production planning based on weather forecasts, artificial neural networks are well suited for because they rely solely on solar radiation and ambient temperature parameters that are readily available from meteorological predictions and enable forecasting future power output. This model does not exhibit any loss of generalization capability, which confirms that is reliable for PV power plant operation planning. As such, it can be a dependable tool for strategic decision making in the management of solar plants facilities. Future research should focus on expanding the set of input variables by incorporating additional methodological and technical parameters such as wind speed, humidity, and equipment condition, such as temperature of model, in order to further impact this model accuracy. Thank you for your attention.
Hvala lepo. Jel ima pitanja? Ja bih zahvalio koleginici i posebno bih istakao značaj ovoga rada s obzirom na orijentaciju na budućnost, jer verovatno znate da kad bi energija mogla lakše da se skladišti, da bi nam sunčeva energija bila dovoljna za kompletne potrebe cele zemaljske kugle i celog čovečanstva, što će verovatno biti jednog dana s obzirom na situaciju sa fosilnim gorivima, tako da zaista vidim jedan vizionarski značaj ovoga rada. Još jednom hvala koleginici, hvala svima, hvala podršci i u što boljem stanju da se vidimo u budućnosti.